Now, this one's a past HSC question, and it is reasonably difficult. I say reasonable, no, it is very difficult because it brings in lots of different areas of the mathematics course here, all into one question. So once we do that, it starts to become harder. So what we've got a parabola here and a line intersecting it at 2 points, alpha alpha squared, beta beta squared, and p some point x squared on that parabola. So the first thing what we want to do is explain why we can get alpha plus beta equal to m, the gradient there, and alpha times beta equal to minus b. So to do this, if we look at the two curves, like x squared and mx plus b are equal at the same points. Well, if we solve those simultaneously, that would give us those values, which just happen to be alpha and beta. So alpha and beta are the roots of a quadratic equation we find when we solve these simultaneously. So we get the mx minus b and minus mx minus b on this side equal to 0. So if the roots are alpha and beta, we know the sum of the roots would be the minus of minus m on 1, which gives us m, and the product would be minus b on 1, so it gives us the minus b. So there's our proof of those first two parts. Next one, we're given this algebraic expression, which is good because you don't have to play around and manipulate from there to there, which means that we're going to use it in the question. And we want to do is show the distance of AB. Well, we know A was alpha and alpha squared, B was beta and beta squared, so we apply the distance formula on those two. So that should have a squared there, because it's alpha minus beta all squared, and alpha squared minus beta squared all squared. Now, we look at that and go, wow, that's pretty ugly, but what we can do is look at what we're given up here and go, okay, well, let's just bring that expression and put it straight there. So we get the alpha minus beta all squared, 1 plus alpha squared, alpha plus beta all squared. So that's okay. We've been able to manipulate that. Now, this is where we start to need to play around because we need to get down to the m squared plus 4b, 1 plus m squared. Well, we know what m is equal to. M is equal to alpha plus beta, and b is equal to alpha times beta. But we've got an alpha plus beta all squared there, and which is okay, but an alpha minus beta all squared, which means we need to do this manipulation. If we remember that from the quadratic polynomial, alpha minus beta all squared is alpha plus beta all squared minus 4 alpha beta. So we need to do that manipulation for alpha minus beta all squared. So that's where that one's come in. Which does work out nicely now because that's alpha plus beta, which is m from the previous question, and alpha times beta, which is minus b. So that gives us the m squared plus 4b. And we had alpha plus beta, which is just m. So we get the 1 plus m squared, which means we've got the expression we want. Okay? So remember our product and sum of the roots from the previous part, and we've got to be careful of the manipulation we get there. Be careful about making sure you use your brackets correctly. Because if you don't use them correctly, it starts to not make as much sense. Even though you might know what you're doing, you're not communicating it correctly, which means you could lose marks there. So be really careful about that manipulation. Don't fudge it. Get it right. The next part says the point there lies on the parabola between A and B, which we saw before. Show the area of APB is given by that expression. Wow. So we've got the base AB, so we've got our base of that. And we just worked out the distance in the previous part. And so what we need is from the x there, because that's B and that's A, we need the perpendicular distance from the x, which is x squared, to that point there. So we know that the equation of that one is mx minus y plus b is equal to 0, because y was equal to mx plus b. And we're going to use the point x squared, so we substitute x in, we substitute x squared in, we've got the plus b, and that would be over the square root of the m squared plus minus 1 all squared, which gives us this expression, mx minus x squared plus b over the square root of m squared plus 1. So our area looks like half times the base, which was AB from part 2, times the perpendicular distance, and took the perpendicular distance, and that was positive there. And so so we get the cancellation of the m squared and the 1 plus m squared there, so those two will cancel out, and we will get the square root of m squared plus 4b, and we've got the mx minus x squared plus b. There. So that's what we wanted. Notice that they're leading you through and giving you all this. So, because the last part of the question then goes, the point is part 3 is chosen, so there is a maximum. Find the coordinate. So all this is leading up to getting an expression that of a in terms of x. Now where we've got to be really careful is that all we're deriving here is the parts in of x. So we're deriving x. M's a constant. B's a constant. So that's just a constant. That's like having like 3 or 4 or pi out the front there. That's just a constant. So we're not deriving with respect to that. So be really careful not to do that. So that just stays out there, and the constant stays out the front. We've just derived this expression here, mx, which derives to m, minus x squared, which goes to 2x. B derives to 0. That's where we get m minus 2x. Set it equal to 0, like we do for any maximum. And m is equal to 2x, so 2x equals m. X is equal to m on 2. Now, if you try and differentiate with all that, and try and treat them as variables and not numbers, it's going to be really ugly. This works out a lot nicer than you only have to derive with respect to x. We get our second derivative, again that's a constant, and we derive that part, so that's just minus 2, which is always going to be less than 0. Therefore, it must be a maximum. And if x is equal to m on 2, y is m on 2 squared, which is m squared on 4. So that's our point, m on 2 and m squared on 4. That's a hard question. That's not pretty at all. And you can see we bring in the work from the quadratic polynomial and the distance formula, so coordinate geometry, and then more coordinate geometry, and then the area of, so working out areas, so some geometry, and then we have a maximum minima. So the calculus then comes into play with our function to prove a maximum or minimum point. So go through the algebra of all that happened and all the concepts. As I said, it is difficult because once you start combining topics, it starts to be a little bit harder. But it's still very doable if you can realise and get away and make sure you understand what M, what B is, what the X's and all the formulas mean.